Hello students, good morning to all of you. Students, in class 11th, unit 5, our today's topic is kinetic energy of rotational motion. Okay, after understood about the kinetic energy of rotational motion, we are discussing about the rolling motion. Okay, so kinetic energy. Suppose we have a particle or a system of particle having n particles. Okay, let's say the distance of each particle from the axis of rotation. This is axis of rotation. Okay, this is the distance of r1, this is r2, this is r3, this one is r4, and the last is r5. Okay, having mass m1, m2, m3, m4 and m5. Okay, therefore the moment of inertia of each particle about the rotational axis is given by I is equal to m1 r1 square, let's say I1, I2 is equal to m2 r2 square, and so I of nth particle is mn rn square. Therefore total inertia of the system of particle is given by summation of mr square. Okay, so if capital M is the total mass and capital R is the radius of gyration of the rotational motion, therefore this is the inertia of the particle. Now when the particle is in motion, it is observed that the kinetic energy of particle is given by, as we know in the previous class, that half m v square is the kinetic energy of a particle in motion. Now we have v square in the form of rotational motion is given by r omega. Okay, where omega is angular frequency. Okay, angular frequency. By putting this value here, we get half m r omega whole square. That we get from here half m r square omega square. Now student, this value is called inertia. That is half I omega square. This is the kinetic energy of rotational motion. Okay, and this we can define as the kinetic energy of rotation, kinetic energy of rotation or rotational motion of a body is the energy possessed by it, possessed by it uh, on account of its rotation about a given axis. Okay, this is the kinetic energy of rotation, and it can also be defined as kinetic energy of rotation kinetic energy of rotation is defined as the half of product of moment of inertia I of body to square of angular velocity omega. Okay, now here I is moment of inertia, which indicates mass of body, or we say inertial mass of body, okay, in equation of kinetic energy half I omega square. Okay, kinetic energy of rotational motion for a n particle system as and for the given axis of rotation. We first calculate the inertia of particles of the body about the axis of rotation. Then by using the formula for the kinetic energy half mv square, by putting the value of v in the form of angular velocity, that is v is given by, or we say linear velocity is equal to the product of radius of circular path and the angular velocity. By putting this we get this result, and this is okay students. Next we have radius of gyration. Okay, so just we understood first the meaning of radius of gyration. Okay, let's see, we have a particle of n particles for which axis of rotation is given. Axis of rotation of each particle is given. Okay, and the particle is rotating about anti-clockwise direction. Okay, let's say some particles m1, m2, m3, m4, mn having respective radius r1, r2, rn, r3, r4. Okay, let's say there is a point on the let's say point P. This is called K or RK, which means radius of gyration. Okay, so the total moment of inertia of the n particle is calculated as m r1 square m r2 square plus dot dot mn rn square. Clear? Now let m is taken as common and we get r1 square, r2 square and rn square. By multiplying or divide n of this equation, we get moment of inertia of n particle about the axis of rotation m into n and r1 square, r2 square, rn square upon n. This is the average of the radiuses of different particle of the body, and here we are using value m k square, where k is radius of gyration. Radius of gyration. Okay, here this k is equal to, we have k square is r1 square, r2 square and rn square upon n. By putting square root of this, we get rn square, r2 square, rn square upon n. This result is called RMS value, which means radius of root mean square value of each distances from this point P about the axis of rotation of the body. This is radius of gyration. Okay, now the radius of gyration of a body about a given axis is equal to the root mean square or RMS distances, or we say root mean square value of radius of the constituent particle of the body from the given axis of rotation is called radius of gyration, and it is denoted by K or RK, where value of K is equal to r1 square plus r2 square plus dot 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 up to n particles square divided by n, that is average of the square of each particle distance. Next, radius of of gyration is depends upon first the shape and size of the body. Shape and size of the body. Second, position and configuration. Position and configuration. Of configuration configuration of the axis of rotation and third part, which is important, distribution of mass of the body with respect to the axis of rotation. These are the factors which affect the radius of gyration of body. Okay, next we have relation between the torque and angular momentum of rigid body. As we discussed in the previous class, the angular momentum of a rigid body rotating about an axis is given by I omega, where I is inertial mass, that is moment of inertia, and omega is angular velocity. Okay, so if we differentiate L with respect to T, therefore dl upon dt is equal to I is constant because mass of the rotating body or moment of inertia is d omega upon dt. Okay, therefore this we get I alpha, where alpha is rate of change of or angular acceleration. Okay, therefore we get the result tau, because torque is given by I alpha. Okay, therefore we get from here the rate of change of angular momentum, or we say the torque acting on a body is measured as measured as the rate of change of angular momentum. Angular momentum. Okay, this is as same as here. I will just interpret the two things. The rate of change of linear momentum dp upon dt equal to f. Okay, that is equal to force, and here dl upon dt equal to torque. So in linear momentum, force as same as in angular momentum as torque. Okay, next we have the principle of conservation of angular momentum. Okay, the principle of conservation of angular momentum, it is most important principle in the rotational motion. Okay, so according to this principle, one minute, according to this principle, when no external torque, okay, no external torque acts on a system of particle, then the total angular momentum of the system of particle remains always constant. Okay, that is if angular momentum of, or if total angular momentum of n particle system is L total. Okay, therefore if the total torque is equal to d L total upon dt for no external torque. Acting on system, acting on n particle system. That is total torque equal to 0. Okay, therefore dl total upon dt equal to 0. That is, we say L total, or we say angular momentum, total angular momentum is a constant. Okay, this is the principle of the conservation of angular momentum. That is L1, L2, up to Ln is constant vectors. Okay, now we understood some examples of or application of principle or based on the conservation of angular momentum. Examples of conservation of angular momentum. Okay, first we have belly dance, okay. Second, spinning volunteer. Third, an ice scatter. Okay, next, springboard driving, spring board diver, etc. Okay, in the belly dance, suppose a belly dancer initially start like this. Okay, so in this case, with the help of the fits, she or he will start to rotate, okay, and balance with the help of his or her hands. When they will get speed, then we have the formula I is equal to mr square and momentum is equal to I omega, that is mr square omega, just understood by this. Okay, so as the radius is decrease of rotation, by doing so the one leg or one foot is touch with the another, okay, and both the legs on the same center, and the hand is closed near to each other, okay, then the radius, initial radius is this, and after closing the radius is too small, okay, but the total mass is distributed on the same place, hence the speed of rotation will increase, okay, because increase in the angular velocity. See, as a ballet dancer here, so suppose a ballet dancer is rotating with her arm and legs, as I will discussed earlier, with stretched onward. In initial case, her arm and the leg is stretched, and as she get the speed, okay, when she folds her arms and bring the stretched leg close to other leg, okay, like this, then the radius of rotation is decreased, due to which its inertia decrease, and as decrease in inertia, angular velocity will increase, okay, hence we observe the rotation also increased in this case. This is the one example. Another I will just explain you that in a springboard diver, okay, in this case when a person is jumped from the springboard, then that time its radius of rotation is too large, okay, when he get the height, then he will close the hand and legs near to each other such that its radius is decreased and the inertia also decreased. As the result, the rotation or angular velocity is increased, hence he can able to rotate 2 or 3 times simultaneously before reaching the ground, okay. Similarly, while jumping a cat, when a cat is jumped, we observed always she will always reached at the ground with their legs, okay, and hence there is no accident with the cat. In this way, she just try to reduce the moment of inertia such that its angular velocity will increase and she will do many rotation and reach with their fits. For example, here a cat stretched its body along with its tails so that the moment of inertia is increased in the initial case, as no external torque is acting, that is moment of angular momentum is I omega is constant. Since I increased, omega decreased and the cat lands gently on its feet, okay. These are some examples of moment of inertia, okay, and which easy to understood about the conservation of angular moment, okay. Next, students, we have some important equation of rotational motion. Important equation of rotational motion. motion. Okay, here students we have velocity or linear velocity is equal to r into angular velocity. First relation between linear and angular velocity. Next, linear acceleration is r into angular acceleration. This is the next relation, that is relation between linear acceleration and angular acceleration. Okay, and next we have theta is equal to distance is equal to r theta. This is the relation between linear displacement and angular displacement. Okay, now so we can use here in place of v omega, because r is constant, in place of a is alpha, in place of d distance is theta. Therefore equation of motion and here equation of rotational motion. First equation is v is equal to u plus at. Here we have the first equation, omega is equal to omega naught plus alpha t, where omega is final angular velocity, omega naught is initial angular velocity. That I will write here, final angular velocity okay, and this is initial angular velocity. Okay, second is u is equal to distance, s is equal to ut plus half at square. Here we have second, theta is equal to omega naught t plus half alpha t square. Okay, and next third one is v square minus u square equal to 2as. The third equation of motion which we have is omega square minus omega naught square is equal to 2 alpha theta. Okay, these are the angular or equation of rotational motion. Okay, now units of theta, omega and alpha. Theta has unit degree. Okay, this has unit rotation per second. Rotation per second. Okay, it is also rotation per minute or rotation per minute. Okay, so rotation per second is called RPS and this is called RPM. Okay, and this is rotation per second square. Rotation per second square or minute square, that is RPS square. Okay, these are the units of angular velocities. Thank you. Students, next we have dynamics of rotational motion. Okay, in this, as we know that work done by linear force F is given by W is equal to F into R, where R is displacement in direction of force. Okay, here in rotational motion the work done is given by torque acting on the body about a fixed axis into a small displacement in angular distance. Okay, let's see. A particle is rotating about a circular path of radius r, and initially it is at A. After some time it reached to point B with an angular displacement theta. Therefore, due to application of force about the axis of rotation in direction A to B, or we say anti-clockwise direction. Okay, anti-clockwise direction. Therefore, the small work done to rotate the body from A to B is given by dW is equal to tau into d theta, where tau is torque on the body. Okay, therefore if first thing, let's say this is equation first, therefore work done is equal to tau into theta. This is the first condition, and by differentiating equation first with respect to time, Therefore we get d omega upon dt is equal to dw upon dt is equal to tau d theta upon dt. Okay, where dw upon dt is rate of doing work, which is given by power, and this is tau into angular velocity. Okay, as p is equal to dw upon dt, that is work, rate of doing work, okay, and omega is equal to rate of change of angular displacement. Okay, so this is the instantaneous torque related to the angular motion or dynamic rotational motion. Okay, as we have power in linear form is force into velocity, here the same formula. Therefore we can say that the value of power as we calculate in the linear form by using force into linear velocity, in rotational form it is equal to the product of torque and the angular velocity. Okay, now here we also calculate the value of torque is power upon angular velocity. Okay, and we can also use one another value of this is power upon torque we calculate here. Now the angular velocity, which is the next relation, this is first, second and third angular velocity is power upon torque. Okay, this is the power associated with the dynamics of circular or rotational motion, that is power is torque into omega. Thank you.